Good day everyone, my name is Edward Wulff.
I'm Jonathan Yan.
And I am Warren Moy. And we are Group A. We designed a force feedback simulator chair. The goal of this project is to design a gaming chair that is connected to a PC through USB. It is connected to a single wall outlet at 120 volts and is supporting up to 350 pounds of user weight while capable of moving in the directions of pitch, roll, and yaw, and more importantly that it is safe. This project can basically be broken down into two major block components, the electrical and computer engineering or ECE block and the mechanical block.
So this is our power supply that runs the whole force feedback simulator chair. This power supply consists of 6 305 watt computer power supplies. We use the 12 volt lines on each power supply and cut out the rest. So when you look into the power supply, we see that we have two power supplies in series. This gives us the 24 volts necessary to run the whole force feedback simulator chair. We have 3 sets of those in series. And then we take those that are in series and put them in parallel in order to increase the amount of current we need. This produces 24 volts and from anywhere from 32 to 36 amps. A key thing to note is that we have to use power diodes in front of each set of series of power supplies because power supplies are not ideal and voltage vary, which would cause current to feed back into the power supplies if the diodes were not there.
So this is our motor controller. It's a Robotech AX2550 DC motor controller with a full H-bridge, which allows forward and backward capability. It has temperature sensing and speed sensing capabilities, but those won't be utilized for this project. So what powers, this motor controller takes in 24 volts DC, plus or minus 10%, and it can go all the way up to 40 volts and supply up to 250 amps for 30 seconds. And how we interface with that is through a serial port, which will connect to the microcontroller block, and then it powers the motor blocks, which is through these 2 separate sets of wires. And so the motors used for this project are the npcrobotics.com brand T64 model motors. They are permanent magnet DC motors. They are rated at 24 volts, can supply up to 1.6 horsepower at 235 RPMs. But for our project, this motor will receive 24 volts DC and up to 18 amps because we have 2 motors and our total current output is 36 amps. And 18 amps is good enough to supply roughly 0.4 horsepower at 210 RPM, which is equivalent to 100 inch-pounds of torque. And through initial testing, that was more than enough to move our design. And as you can see here, this is what's going to be attached to the motor. It's a mechanism wheel that will move in both directions, allow forward, backward movement, and side to side.
So this is our speed sensor. We use a magnetic sensor in order to determine the position of the motor. How this is done is we use a magnet and place it at the end of the shaft. And we place the speed sensor right next to the magnet, and as the magnet rotates, the sensor is able to determine the direction or position of the magnet, giving us RPM. So what I'm holding here is our motion sensor. We have 2 motion sensors that are placed on the bowl of our chair. We use these motion sensors to determine the yaw, pitch, and roll of our chair. So how that works is we use two triple axis accelerometers, and determining the position of the bowl we can determine roll and pitch. And using the relative motion of 2 motion sensors, we could determine the yaw. And this is all done through relative motion and the effects of gravity.
We selected the TNC++ 2.0 as our microcontroller. It has a very easy to learn, very easy to use platform for coding. TNC++ has a built-in USB serial which receives string byte commands from the PC. These string byte commands are input into this microcontroller, in which the code uses polling currently, a series of switch statements, if statements that compares the input with a match. Once a match is found, that input is translated into a string byte that the motor controller understands. So it outputs that translated string byte command through its RX and TX serial pins and ports to this MAX232 circuit. This MAX232 circuit is responsible for converting TTL signals to serial signals. TTL signals are basically 0 to 5 volt range, serial signals are negative 12 to 12 volt range. So one, it allows them to communicate. Two, it protects the TNC++ from damage and harm that the serial might cause it. And this board has 46 digital input and output pins and ports. And of the 46, we are only using 10 of them. 6 for the speed sensors and 2 for the motion sensors, and then 2 for the RX and TX to the motor controller. But for the speed sensors, we have 2 channels, 1 and 2 for each of the motors, and we're only using 3 pins for each motor. 2 channels remaining for the motion sensors uses the TWI, the SDA, SCL pins and ports of the TNC++, and that can be connected to 2 channels or even more through the whole multiple slave process for the TWI protocol.
So right now we are showing you guys how the bowl would move if we had motors in. We're going to use me and John to move the bowl, and we'll show you the different types of movements.
Show me yaw! Show me pitch! Show me roll!
We were not able to show you moving the bowl with our motors because we ran into several mechanical problems. The first thing we ran into is the actual bowl. It was hand sanded by the 3 of us, and because it was hand sanded, it does not form a perfect sphere. Not having the perfect sphere underneath the bowl prevents having a grip on the bowl at all times with the motors, meaning that at one point the bowl will get stuck because the motors are no longer moving the bowl.
The problem that we had was the placement of our mechanism wheels. They tended to always not or lose contact with the surface of the bowl, and placing the mechanism wheels at the right height is an art within itself, and it's nearly impossible to get right with our hand sanded bowl surface.
Another thing that we discovered was that we were limited in the amount of tools that were used in order to produce this.
So for our unique design considerations, in order to make our bowl platform move, we had to come up with a system of ball bearings that would contact the surface of the ball evenly all around. But a problem that we had was that the ball bearings would not all touch the surface. So we had to develop a suspension type system for each one of the ball bearings. I'm unable to push it down, but the weight of the bowl will be able to. And another consideration that we had to think about was the portability of our overall design. So the way we designed it was that each piece you could take each piece out of here by undoing each one of these stands, like so, and then you should be able to lift up this entire piece. Pretty much all the components in our project is modular. So as you can see here, the power supply, you could remove it completely from the system by disconnecting a couple of terminals. And then the motors themselves have housings that you can take out completely, along with the motor controller, where you could just completely disconnect.
Here's some useful hints for senior design next year that will help you manage your projects well, and it'll help you be successful next year. One useful hint is that you should not make your projects too complicated. Making your projects too complicated will spread your time thin, and time is a limited factor when it comes to senior design.
So speaking of time management is a big factor that we had to deal with for this project. In the end, just don't on things last minute, and in the end you'll realize that you actually have less time than you really do, and it's a scramble.
If you really want to manage your time correctly, don't be afraid to ask for help. Just because you're a student does not mean you should know everything. Ask for help when you need it. Ask your peers, ask your senior design instructor, ask your professors, because it will save you a lot of time and work.